Hi everyone. Today we're going to start our first short lesson on Chapter 20, which is dealing with electrochemistry. And when we're talking about electrochemistry, the key part of that is electro, meaning electron. So in electrochemistry, we're going to be focusing on the movement of electrons. In this section, we're going to be reviewing oxidation states, which hopefully you remember from earlier in the year, and what entails a redox reaction. And I'm going to say redox, that's kind of the shorthand way of saying it, but the proper way is oxidation, reduction, reaction. After this video, you should be able to determine the oxidation number of each element participating in a chemical reaction, identify what is being oxidized and what is being reduced, and identify the oxidizing agent and the reducing agent. And as I said, hopefully this section is mostly reviewed to you. What are oxidation numbers? Oxidation numbers tell us the extent to which something has been oxidized. You might remember that oxidation is losing electrons and reduction is gaining electrons. The mnemonic device is oil rig. Oxidation is loss, reduction is gain. So an oxidation number or oxidation state tells us just how many electrons have been lost or how many electrons have been gained if an element has been reduced. So to keep track of what loses the electrons and what gains the electrons, we're going to assign oxidation numbers, also called oxidation states. So here's the example we're going to be looking at. We've got some concentrated HCl down below, and you know that's a strong acid. And then we've got a metal above, in this case zinc powder. And so hopefully you would be able to predict the products of this single replacement reaction, of course checking the activity series to make sure that it will go, which it will. So if the oxidation number for an element increases, that element is oxidized. So what does it mean for an oxidation number to increase? Well, we can see that an element is in effect becoming more positive. And it's becoming more positive because it's losing electrons. So this makes sense. On the other hand, if the oxidation number decreases, we call that reduction. That element was reduced. And the word reduced literally comes from the fact that, for example, we could go from a 5+ oxidation state to a 3+ oxidation state. So the literal number went down. And the only way that it could have gone down is by adding electrons, by gaining 2 electrons in this case. So let's take a look at our zinc and HCl. Hopefully you predicted that we would make zinc chloride and hydrogen gas, and it's also a highly exothermic reaction being a strong acid. Okay, can we identify what was oxidized and what was reduced? And this is why oxidation numbers are so important. So you might recall that an element in its standard state is going to have an oxidation number of 0. So that makes the hydrogen product also 0. Don't be confused that it's diatomic hydrogen. It's still an element in its standard state. You might recall that most of the halogens have an oxidation state of -1. Hydrogen is typically +1, although not always. And if you notice, my oxidation states for this HCl molecule add up to 0, which they should. And if we finish this up on the right, the chlorine still has a -1 oxidation state. Don't be confused. I know it says Cl2. Do not distribute the 2. We're looking for the oxidation state of the element and not the overall charge of the anions in this compound. But we see that since we have 2 of the -1, so we've got -1 and we've got times 2 of those, and we know that zinc chloride has to add up to 0 overall, the missing number must be +2. So can we identify what was oxidized and what was reduced? Yes, we can. We can see that the zinc was oxidized because the oxidation number went up. It became more positive. And it's a great idea to label, just like I did here, your 2 species that became oxidized. The hydrogen started out as a +1 oxidation state, but became a 0 oxidation state. That is reduction. We're going to be calling these later in this chapter half reactions. So we have the oxidation half reaction where zinc lost its 2 electrons, and we have the reduction half reaction where the hydrogen ion, the proton, gained electrons so that it could become hydrogen again. So hopefully this is coming back to you about oxidation numbers and how to figure out whether something is oxidized or reduced. Let's quickly review the rules for assigning oxidation numbers. Number 1, pure elements in their standard state have an oxidation number of 0, even for the diatomic elements. If we have a monatomic ion, such as Na+, the oxidation number is the same as its charge. There is a difference between oxidation numbers and charges. We tend to use them interchangeably in chemistry, but when we're talking about redox reactions, we need to be careful to talk about the oxidation number and not the charge. Fluorine is always -1. It's the most electronegative element. It is always going to gain 1 electron. Oxygen is -2, except for this strange ion, peroxide, which you remember is O2 with a 2- charge. So we've got 2 oxygen atoms, and between them they've gained 2 electrons. So we could consider then individually they've kind of gained 1. So that means the individual oxygen would have an oxidation number of 1. This helps us understand why peroxides are so reactive. Oxygen is the second highest electronegative element in the periodic table, and it is not content with gaining just 1 electron and sharing with its buddy. It is much more likely to gain another and become O2-, which is consistent with what I told you over here. Hydrogen is +1 unless hydrogen's bonded to a metal, for example, sodium hydride. In this case, the hydrogen must be the thing that gained the electron from the sodium. But in most circumstances, hydrogen is going to be +1. Halogens are typically -1. So all the group 17 are -1, unless they're bonded to oxygen, in which case you'll have to figure out the charge of that halogen. So this is perchlorate ion, Cl4 with a 1- charge. In this case, although chlorine is pretty electronegative, oxygen is more electronegative. And so we know that each oxygen has a 2- charge. And we're wondering what number, when added to 4 times -2, will give us -1. And that number is +7. So in this example, chlorine is a +7 charge. And finally, the sum of the oxidation numbers in a compound or a polyatomic ion must equal the overall charge. And this is probably the most important one of all, because with that rule you can determine the oxidation number of whatever is missing. So all the oxidation numbers for a compound overall must add up to 0. Don't forget to distribute based on your number of atoms. For example, H2O, hydrogen's +1, oxygen's -2. Uh-oh, that doesn't equal 0 when I add them. Well, it does when I remember that hydrogen is 2 times +1, and this one's -2, so that gives me 0, which I expect for a neutral compound. Oxidation and reduction, we just talked about this a bit. A species is oxidized when it loses electrons. Oil rig. So in this case, we can see that the zinc has lost electrons. It went from zinc with no charge to zinc with a 2+ charge. We could also say the oxidation state of zinc decreased from 0 to, it increased from 0 to +2. So zinc lost 2 electrons, forming the zinc 2+ ion. That is oxidation. Something is reduced when it gains electrons. In this case, the oxidation number of hydrogen ion was reduced from +1 to 0. Oxidation and reduction must occur together. Why? Think about that for a moment. So if something is to lose 1 or more electrons, something else has to gain 1 or more electrons. They can't just fly off into space. They don't just disappear. So oxidation and reduction must occur simultaneously, and this is going to become very important in the next couple of sections of this chapter. An oxidizing agent is the thing that causes oxidation. A reducing agent causes something else to be reduced. On the AP Chemistry exam, they are not going to be using this terminology because they think students are too easily confused by it, because the thing which is oxidized is the reducing agent, and the thing which is reduced is the oxidizing agent. The problem is everyone else in the scientific world is still going to use these terms, oxidizing agent and reducing agent. So you need to know them. You're not going to see those words on the AP exam, but you're absolutely free to use them in your free responses if you need to, as long as you use them correctly. So the oxidizing agent causes something else to be oxidized, which means loses electrons. So that oxidizing agent must be reduced because it is gaining electrons, and vice versa for the reducing agent. Okay, let's tackle a quick practice problem. A NiCad battery, these are the old types of batteries that used to be in the really old cordless phones. They never really worked very well, so now we don't really use this to make batteries anymore. But here's how it worked. There would be cadmium metal and also nickel metal in the form of an oxide or a hydroxide. And we're going to look and see if this is a redox reaction. Well, first of all, it says it's a redox reaction. So let's figure out what is oxidized and what is reduced. And in order to do this, I'm first going to have to do what? I'm going to have to put in my oxidation numbers across the whole reaction before I can reliably detect what is being oxidized and what is being reduced. So I recommend pausing the video for just a moment, try to put these oxidation numbers in, and we'll see if you got it right. Okay, so first of all, cadmium is going to be 0 because it is a pure element and it is in its standard state. Now, nickel with oxygen here, I'm going to start with the oxygen, and I know that it's 2 minus. Don't be confused here. This is not an example of peroxide, and I'll show you in a moment why. 2 times negative 2 gives me negative 4, so in order to balance that out, I have to have positive 4. So nickel is positive 4. Let's take a look at water. Oxygen's minus 2, so in this case, each hydrogen must be plus 1. Don't be confused by this coefficient. That has nothing to do with the oxidation state right now. Cadmium hydroxide. Okay, well, we've got a metal. Metals can have many different oxidation states, so let's start with something more comfortable. Here's our oxygen, and we see that hydrogen is bonded to oxygen, so that's going to make the hydrogen plus 1. Okay, and also this makes sense because that looks like hydroxide to me. So 2 plus, 2 minus plus 1 plus add up to minus 1. So that makes sense. All right, here's where we need to be careful. We've got 2 of the hydroxides. Each hydroxide has an overall charge of minus 1, and so the cadmium in this case must be 2 plus. Finally, if we assume that the hydroxide is the same over here, then the nickel must also go to 2 plus. And now that we've learned about spontaneity, we know that this reaction is spontaneous in the forward direction up until a point. What happens after we've used this battery too much? It goes dead. Well, we say it goes dead, but that just really means that Q equals K. It's at equilibrium. How are we going to reverse the equilibrium to get it back to its recharged state? Well, in the forward direction, if that produces electricity, then we can stress this in the opposite direction by adding electricity back into the system. So we will use electricity to do work on this system to make Q, once again, less than K, so that when we need to use the battery, it is charged up again. Unfortunately, these old style of batteries really didn't hold their charge very well at all. All right, let's look and see what is oxidized or reduced. We are looking for any changes in an element's oxidation number. I don't see any changes for any of the oxygens. I don't see any changes for any of the hydrogens, but what I do see is that cadmium went from 0 to 2 plus, and that is oxidation because it lost 2 electrons. And nickel was reduced because it went from 4 plus to 2, 4 plus to 2 plus. That is reduction. So cadmium was oxidized, nickel was reduced. Go ahead and take a moment and see if you can identify the oxidizing agent and the reducing agent. So the reducing agent is the thing that caused reduction. Nickel was reduced, so the thing which caused nickel to be reduced was actually cadmium. So oxidize is the same as the reducing agent. The oxidizing agent caused oxidation, so that means it gained electrons, it was reduced. The oxidizing agent was nickel. So just keep in mind that, that the words are actually opposites of each other. All right, now it's your turn. What is the reducing agent in the following reaction? Is it bromide ion, hydrogen peroxide, hydrogen ion, or diatomic bromine? So take a moment, ponder this, and we'll continue. Okay, well, once I assigned my oxidation numbers and looked for the changes, I would find that bromide ion was the reducing agent. So if you need more practice on this, see sample exercise 20.1 in your textbook. So after this short video, you should be able to find out the oxidation number of every element in a chemical reaction, identify what is being oxidized and what is being reduced, identify the oxidizing agent and reducing agent, and that is all. So good luck.